So anyway, it's not been, I've not taken off just to see how you are approaching the problem. So only that's why I'm not taking off too many points, one or two, if it is not matching. But if it is more, then there may be something else is also missing, not just that. Because see, there some of the things were fairly obvious, size of the sensor and all. That was should have been the ETA. So that those लिखा था मैंने मिस कर दिया तो बता देना मुझे।
मैंने ये नहीं लिखा कि this should be the size of sensor. So वो
तुमने केवल ईटा ही लिखा है ना? हाँ तो ठीक है। ओके, नाउ आई एम गिविंग यू, कितने लोग आ गए? आर एनीवन मिसिंग? इज एनीवन मिसिंग हु विल टेक द एग्जाम? प्रोबेबली यस। सुमित नहीं है। सो देयर इज अ क्वेश्चन व्हिच आई एम गिविंग now, which you have to go and do at home. That will, some part of that will come directly. So some data of that will be needed. So basically, small part of question for minor. For अब तो मिड सेमेस्टर बोलते हैं ना, नाउ वी डोंट कॉल इट माइनर. Take a cup, fill it with water. Okay, and then first thing you do is measure the diameter of the cup. All of you have a scale, you can easily do this. Secondly, stir the water with spoon जैसे चाय मिलाते हैं we are, but you do it in circular motion. You can also do it like this, but we do it in circular motion. Now what I want you to do is count. So do it for 1 minute. Number of revolutions made in 1 minute. So this is a simple, that's all. So I will ask you these two things. What was the diameter of the cup and how many revolutions were you able to make in 1 minute? And maybe then some more processing after this. So this, possibly all of you will have unique answers. It's possible two people may have same. So, and this need not be, you don't have to be very accurate. 10.2, just give it in whole numbers. In a time, you should have an idea that when you stir tea, how much RPM it is. At least I had no idea till I did it myself. And it turned out to be not so low. So just, and these things I will ask in the exam, and you have to start from here. This will be the starting point in one question. समझ गया कि नहीं? I guess इससे question भी guess कर सकते हो. Maybe I'll ask you to make a question based on this. ठीक है, it's obvious, बहुत ज़्यादा चीज़ें नहीं है, but these two things I want you to have your own numbers and you should have an estimate. So basically घड़ी ऑन कर दो, बस गिनते जाओ, जब 1 2 3 4 5 6 1 मिनट में कितना किया. Of course, those who are stronger will probably have more revolutions. Old people like me will stir it slowly. So whatever. So these two things you should bring when you come to the exam. ये numbers लेके आने हैं. They will not be provided and you have to use your own numbers. See, the reason I am asking you to do this is that if I could have straight away said in the exam, you assume a diameter of the cup, you can always assume. You know it will be what, 6 centimeters, 7 centimeters, 10 centimeters, not more than. It won't be 1 meter. If you write 1 meter, then it's a wrong estimate. And you should not be doing that. And similarly, when this is something which at least I had no idea, and then when I started, मैं हवा में ही करने लगा, मैंने कहा 1 मिनट में देखो तो it turned out to be quite large. It's not, मतलब I thought it will be 10 RPM or something, but it turns out to be bigger. And हवा में से ज़्यादा होगा तो just do it. I think that will take you just 2 minutes. Stop watch on करके या घड़ी में ही 1 मिनट देख लेना. I could have asked you to do it in the exam itself, but then some people will say मेरी घड़ी नहीं थी, मेरी घड़ी में stop watch नहीं थी, ये था वो था. So that's why I said you do it at home and bring these, and you will get some credit for this also. 1 out of 100, 2 out of 100, whatever. ठीक है. अब कौन नहीं आए हैं? Do you know anyone who has not come? Sumit, who else? 14 people are submitting things. 1, 2, 3, 4, 9, 10, 11. So, Ananya and Meet. अनन्या क्या AM का है कि ME का है? तुम जानते हो?
हाँ, वो बस तो बहुत टाइम से नहीं आ रहा.
बहुत टाइम से नहीं आ रहा? क्लास में काफी टाइम से नहीं आ रहा क्या? तो विड्रॉ मार रहा है तो मार ले भैया, बता दे मुझे. अच्छा है. और अच्छा, तो मे बी ही इज नॉट इंटरेस्टेड. एंड व्हाट अबाउट मीत? तो आ रहा है, ही कीप्स ऑन कमिंग. सो एनीवे, तो मीत को कोई जानता है क्या? बता देना. सुमित, इज एनीवन इन टच? So at least tell him that this has to be done, or let him look at this. Number 2, calculators will be needed. Will not allow you to use watch or a device. So you have to bring calculators. And also another thing that I realized is that if somebody gives me a new calculator, I just don't even know how to use it. So bring a calculator you are familiar with, because here we have all these powers to the 3/4 and 2/3 minus 5/3. So all those calculations may be there. So you should know how to carry out those to the power things and all those. So calculators will be needed. रूम नंबर आया? अभी भी नहीं आया. 1 दिन पहले आएगा. अच्छा, हो सकता है हम लोगों के पास आ गया. एनीवे, now as far as the homework number 1, see, you may have realized that things were sort of, many questions were quite open-ended type of thing. So, in particularly the 4th one. So 4th one was not this highest frequency thing is what left you very foxed, but most of the people. But again, I'm not very sort of how they get it with the. I think what he has probably tried to do is look at the biggest velocity scale and the smallest time scale, divided the two, and that gives the. Now the logic for that, because on one way you may also feel that the anemometer is fixed on the plane, so therefore this velocity of 50 meters should not affect. That may have been the logic for taking 1 over eta and not, or the velocity of the cloud divided by eta. But because this is also, the plane is also moving with 50, so.
So the various fields, like you only do operations between similar scales. Similar scales in the sense that you didn't teach us anything about, let's say, taking the interior velocity scale and dividing it by the Kolmogorov length scale. Because that just didn't make sense. But here for the frequency thing, they have done just that. Like,
So
why doesn't it make sense to just do it 1 upon tau, where tau is the Kolmogorov time scale? I mean, I understand
No.
it will give you the largest value, but
I think
The frequency, I think, means the rate at which the instrument will sample the data.
yes.
So the airplane is moving at 50 meters.
Okay.
per second, I think.
Yeah. Here.
And the length scales of the smallest radius are the eta.
Yeah.
So how many eta will come in 1 second?
Okay.
So 50 divided by the
Ah.
eta
Ah.
will be the number of eta that will come.
हाँ.
So that is the frequency at which it should sample. That is the
Yeah. So ठीक है. So these are, as I said, don't. This is just an open-ended type. Some of these questions may be like this. Also, what we wanted to see, मतलब, like for example, there's one question where I have just given you, if you have attempted, I have given you the credit where it says about the wall part. But if I have not attempted, I have taken 1 mark off. So I've not even checked whether it is right or wrong. I just wanted to see I think that's in question number 2. So where the U was asked and then he says what happens near the wall. So if you've written something, I've just given you the point. So this is just to see what happens is in a typical boundary layer, the length scales, if it's not turbulent, that we have seen also goes like square root of nu t, the cross length scale. So I think that is what they were trying to see there. So basically, in questions which are open type of thing, just try to analyze it in what you think is right and then put that. That is what we are looking for, trying to develop your thinking. Okay, of course, some of these questions, some were quite straight, which had to have this thing like, another mistake a lot of people made, which was probably unintended, was this E of k was written as, what? See here, E of k is equal to k to the power of -1 times v square of k. Now, some of you took this as v square being multiplied by k and got the wrong result. It is v square. See, at least the way it was printed, it was clear that because even in E, it is E of k. So this was a function v square depended on k. That is what was. So I think that's why some people have got this wrong, because of taking it as v square multiplied by k, which is 1 over r. So then obviously it becomes wrong. It is just k 1 by k times v square. So if you have taken that, then most of you have got it right, but that was the other thing. Anything else in the...
I do not understand the
permissible noise level part? This. See here, I think what is being done is this basically they've taken a ratio of the velocity to the this thing, smallest fluctuating velocity. Isn't it? That's what seems to have done, because no, it is 2.3 into 10 to the power of minus. Noise level of this, even the smallest fluctuations. The velocity scale is given. Now, noise scale is 1.2 into 10 to the power of minus, the smallest velocity scale. Now, what he is saying is, if the circuitry must detect a signal of this superimposed on 50 meters per second. So that means this velocity is 50 plus minus 1.2 into 10 to the, so that's this thing. Then what is the noise level? So noise level, then he is finding it as, actually, is it 1.2 into 10 to the power of minus 2 divided by 50? What would that give you? नहीं तो नहीं होगा ना, इसका परसेंट. अच्छा, उसका परसेंटेज निकाला लगता है, आई थिंक 2.4. 1.2 divide 1, I think that's what he seems to have done. Even I wasn't. 1.2 into 10 to the power of minus 2. See, this is the u prime, this is the mean of u. And then he has expressed it as a percentage. तो वो तो आई थिंक काफी मैंने शायद चेकिंग में कुछ कपला किया क्या, आई डोंट नो, मे बी आई हैव नॉट. See, because the noise means whatever is the fluctuating part of the velocity divided by the mean velocity, by the velocity. So that, and I think expressed as a percentage.
So, question you have written function of K mass product. Whatever it is.
That's what I was just explaining ना, that this v square is not v square multiplied by k. अच्छा तो बाद में देख ले. नहीं तो you would have got 5/3. Now you're not getting 5/3. If you would have done that,
So
I thought you would.
like I've just reduced it to epsilon upon K4 to the power 1 by.
नहीं तो बट तो ये -4/3 हो गया ना. ये कितना हुआ ये
Okay,
-1 and -4/3 will be -7/3. So yeah,
Okay, I think the mistake is I haven't squared this.
अच्छा देख लेते चलो. हाँ ये v smallest velocity. हाँ I think now I understand. मैंने भी grading कर दी, but most of you have taken it as u prime upon u, not v eta upon u. That was the mistake. Noise level सबने ठीक किया, but ये v prime it should have been u eta upon u. Smallest velocity scale. Most people have taken u prime upon u. V eta upon u, because again the same logic that if it has to the smallest velocity scale the anemometer will encounter will be v eta.
What is the permissible noise level?
हाँ
The maximum noise level that we can.
permissible noise. Can anyway again this one, even that's not my. चलो okay. तो ये हो गया. Now continue with vortex dynamics. We are, as I said, so now we look at the हाँ असाइनमेंट अपने हाथ के लिखे हुए ला सकते हैं. तो जो ठीक करना है इसी में ठीक कर लेना. असाइनमेंट्स एनीथिंग हैंड रिटन आई सेड हैंड रिटन चीज हो सकती है जेरोक्स ऑफ हैंड रिटन इफ यू हैव मेड नोट्स एंड बट मतलब खुद लिख लोगे ज़्यादा अच्छा है. आई थिंक दैट इज व्हाट. दूसरे के जेरोक्स मत ले आना. आई एम नॉट इट्स नॉट बट वो समझ में भी नहीं आएगा ना, फिर वो नोट्स ही ढूंढते ही रहोगे दूसरे के जेरोक्स में. At least if they are your notes, you'll know what you did when. Where did you write CF? This, somewhere we talked about drag coefficient C for laminar flow versus turbulent flow. अगर खुद के लिखे हुए हैं तो तुम्हें पता है कहाँ है. दूसरे के you'll keep on turning 50 pages. Where is C? You'll not be able to locate it. Okay. So now we look at the Navier-Stokes equations, and now what this part which I am doing now is something which actually would have been done in a course in fluid mechanics, at least those who did the fluid mechanics, even 106 with me. Some of this was done there in maybe in a different form. So let's write the Navier-Stokes equation. Navier-Stokes equation is now capital U was instantaneous, so dy by dt So here what I have done is actually we write it as uj dui by dxj, but because of continuity I have taken it inside. So incompressible flow. This is this. So now we look at the term d by dxj of ui uj. This again anyway uj dy by dxj. This is anyway what the term was without the continuity. Now from there what I do is I subtract uj duj by dxi plus uj duj by dxi. So this second and third part I've just added and subtracted. Why I am doing this? Because now uj is common and I get rij. I want to get things in terms of omega. So dui by dxj minus duj by dxi will be 2 times rij. So I want to get that and then I have a second term. So I do this. So this becomes equal to two uj small rij plus, and the second term, this term, I will write it as d by dxi of half uj. If I take the uj inside there, then this is d by dxi of uj. So d by dxi of half uj is uj duj by dxi. So I've just played this trick. And rij, I can write it as minus epsilon ij k uj omega k. नहीं हाफ था पर वो टू एक उसमें ओमेगा और आर आई जे जब रिलेट करते तो एक टू होता है रिलेशन में. अंदर हाफ था ये वाला, हाँ हाफ, अच्छा ये वाला सॉरी के, हाँ मतलब हाफ तो होगा. ठीक है. नाउ द विस्कस टर्म, again we can play some games with it. Basically I'm trying to introduce omega. So in the inertial term I have introduced omega like this. This was the inertial term, so it becomes minus epsilon I j k u cross, or it is equal to minus of u cross omega, and plus partial by partial xi of the kinetic energy, ui, uj, or whatever. And the viscous term becomes, now viscous term when we look at it, this was nu times this can be written as nu times d by dxj of dy by dxj minus duj by dxi, and then plus I have to add nu times d by dxj of duj by dxi. क्योंकि ये हमने ये तो dy by dxj था, d by dxj एक तो बाहर ले लिया. हाँ ये वाली वो दिखा रहा हूँ जीरो, that is my next argument. Now this term will be zero, जो plus part. See first I had d2uy by dxj. मतलब you can probably get it in other ways also, maybe it's a tedious way. So d by dxj of dy by dxj था, उसमें माइनस किया और प्लस किया, और जो सेकंड पार्ट प्लस किया इसमें duj by dxi है बट d by dxj है. सो d by dxj अंदर गया तो duj by dxj आ गया. सो कंटिन्यूटी से जीरो हो गया, और ये पार्ट ये रह गया, और ये पार्ट क्या है, dy by dxj duj by dxi 2rij. So this becomes equal to, so this is equal to 2 nu r को ठीक लिख देता हूं मैं, 2 nu times drij by dxj, and this I can write it as minus nu times d by dxj of epsilon ij k omega k, and this becomes minus nu epsilon ijk is only 0 and 1 partial omega k by partial x. तो इसमें rij is epsilon ijk omega k with 2 and a minus sign. So then, so then this becomes minus q nu d by dxj epsilon ijk omega k, and then epsilon ijk is just zeros and ones can be pulled out, minus nu epsilon ijk d omega k. So that means basically we have put every two terms in terms of vorticity, and now when you club in, then this term will become this d by dxi of half uj can be added to the pressure term, plus because both have d by dxi. The original equation में थोड़ा सा और चले जाता हूँ. So it's a d by dxj of ui uj जो है बेसिकली मैंने ये j और i का d by dxj लिखा है of ui uj. सही है ठीक है. Okay. So this is one. So it's d by dxi of p, and then this part will be d by dxi of half uj. So that I can put in one bracket, and the second term will become this minus epsilon. So will become in terms of omega, and this term will also come in terms. So when we club in everything, so what we get is, so again this is all instantaneous velocity, no turbulence, nothing is assumed. Partial ui by partial t is equal to minus d by dxi of, we had a capital P, isn't it? Or capital P tha. P by rho plus half uj plus now one term came epsilon ijk, uj omega k came from the first term, minus nu epsilon ijk d omega k. So this is the term which we get. Now, does this term remind you of something? P by rho plus half uj. Bernoulli equation. Okay? P by rho plus half v square plus gz is equal to 1. In fact, g is also buried in P. So that means one thing we realize is if the flow is steady and if omega is 0, then Bernoulli's equation is valid. And actually this is one thing which one does, that when you, in the basic course, when we derive Bernoulli's equation, then we get the condition steady flow, incompressible flow, and then we say either it has to be applied along a streamline. If you apply it along a streamline, then these two terms will go away. Okay, and actually, and otherwise it can be applied anywhere between 2 points only if the flow is in rotation. If omega is not 0, then Bernoulli's equation, if the flow is in vicinity has to be there, can be only applied along a same streamline. But if omega is 0, the flow is steady, then you will just get P by rho plus half uj is its gradient is 0, so therefore this must be a constant. There are many forms, and unsteady form says, that means then you say this is a function of t, and this u we write it in velocity potential, it becomes partial phi by partial t or something, but that, so you get different forms. But this is basically, so here if omega k is equal to 0, we get Bernoulli equation. Now, let's look at this term, epsilon ijk uj omega k. This is one term which is coming. Now, this is equal to, if you look at it, this is equal to u cross omega, because epsilon ijk is a cross product, uj omega k, so u cross omega. Okay. Now, have you seen U cross omega in physics or when we derive equations of motion? It is actually what we see as a Coriolis force. If we write our Coriolis acceleration, actually it is. And if we write our equations in a rotating frame, then it comes on the other side as a force. And the Coriolis force is 2 omega cross v. Now, it is omega cross because when you take it as a force, it goes on the other side. So, it becomes 2, and the 2 comes because this omega vorticity and the angular velocity are related by a factor of 2. So, the 2 goes away, but basically this term is this term is the same as the Coriolis force in a rotating frame of reference. Actually, saying Coriolis force is technically not correct. It is an acceleration. At least the undergrads who are here, you have seen, you must have done that in detail. This thing, they are nightmares of a course, APL 100. Well, some of you may know it's my favorite course. But there we do this term Coriolis acceleration. But certain things to realize what, and again we'll try to see if I expand this epsilon ijk omega k. So this is ijk, if I write this u cross omega. So this will be u1, u2, u3, omega 1, omega 2, omega 3. And let's look at the one component of u cross omega. What will this be? The I component. u2 omega 3 minus u3 omega 2. Okay. So this is u2 omega 3 minus u3 omega 2. Now, let's physically try to see if this is 1, 2, and 3 direction. This is my coordinate axis. Omega 3, or first let's look at u3 omega 2. So omega 2 means a spinning vortex which is spinning about omega 2, about the 2 axis. This gives me omega 2. See, omega 2, it's spinning about 2. Try to think physically. So this is omega 2. And on this u3 is acting. u3 means the velocity which is coming out from inside the board to this. Okay. So u2 times omega 3. And what is it doing? It is applying a force of minus u3 omega 2. So that means this will put a force on this which will be equal to, in the one direction, it's spinning like this, and the velocity 3 which is coming from the third direction. Together, they will put a force in this direction, in the minus x1 direction on this vortex. Why? Because this term, if you look at du by dt, is acceleration which will be equal to force. So this is coming there. So this u2 omega 3 means that on this there is a force F2 force, or maybe I'll just show it as a single vector, minus u3 omega 2. So this is omega, and is there a minus sign in front of this? Let me just see. There's a minus also. There's a minus, I missed that minus sign. So because of this, so this is u2 times omega 3. So u3 is coming like this. This is omega 2. And together because there's a minus sign also, so they cause a force F1 here, which is equal to एक मिनट रुको. In the final equation कहाँ है मेरा? No, it's epsilon ijk. There's no minus uj omega 3. So this force on this vortex is minus u3 omega 2. ये मैंने बहुत ही गड़बड़ किया. First, let's keep it this way. Now let's see, it's minus u3 omega 2 and the term is epsilon ijk omega k. So this causes a force ये क्या हो गया इसको of F2 is equal to minus u3 omega 2. And there's another vortex which is u2 omega 3. So there's a vortex with omega 3 and a vertical velocity u2 which comes on this causes a force F1 which is equal to u2 times omega 3. So these are the type of body forces which come on an element because of an interaction of omega and u. Okay? So if there's a vertical element like this, and because of this velocity, it gets a force in the x direction. And similarly, a vertical element in the 3 direction, because of velocity u2, will get a force in the 1 direction. So these, and now in Coriolis force, when we talk of rigid body, then of course we have a body with a particular omega. Now this is a fluid, so every element can have any omega. So all the elements have forces like this. And when we look at this F2, because the velocity is in the u3 direction, what type of a force is it? Drag or lift, if we just want to call it in that terminology. See, this F2 is because of u3 and the force is in the x1 direction. It will be a lift type of force because it's perpendicular to the velocity. Of course, we don't normally when we talk of drag and lift, there is only one component of velocity, and then we talk of. But if I look at locally for this element, this is like a lift force, the Coriolis component, and these are like a body force which are acting at every point in the fluid. Similarly, there will be there are 2 components, there are 3 components, all of them will be there. This is just to illustrate and show how these sort of forces could come in. So this is the body force which comes in because of the Coriolis component. Now, so far this was our equation. Now what we do is, if we expand or if we write omega I is equal to mean of omega I. कल मैंने ये यूज किया था या छोटा यूज किया था? I don't know. नहीं, पर फिर मैंने कहा था विल स्टिक टू वन. ये यूज किया था ना. तुम्हें बड़ी प्रॉब्लम हो रही थी, आप एक नोटेशन क्यों नहीं यूज कर रहे हैं? मुझे भी यही प्रॉब्लम हो रही है, व्हाई आई एम नॉट यूजिंग वन नोटेशन. आई यूज दिस ओनली ना, कैपिटल ओमेगा. ठीक है, फॉर मीन. सो नाउ if we assume, क्या हो रहा है? पेन नहीं चल रहा. Steady flow. I'm having a bit of a problem with the pen today. Assume steady flow and take mean of UI equation. So that means I'm taking mean of, let's have a look at this equation. So if it is steady or stationary flow, this term will give me 0. When I take the mean of dP by rho, this term, let's see, it is uj, so it will give us k plus a mean of k, d by dxi of mean kinetic energy and the fluctuating kinetic average, because it's uj, so it's uj plus uj prime. Then when you take the mean of the whole, mean uj plus uj prime, and the other two will become 0. Then we have this term epsilon ijk. So now this is uj omega k. So mean of uj, again similar, mean of uj, mean of omega k, and mean of uj prime omega k prime. The other two terms will go away because one mean and one fluctuation. Okay, and this term will just become mean, because this, see, always you realize in equations when you are averaging, the non-linear terms are giving the Reynolds stress type of terms. The linear terms just average out as it is. Doing the exercise also you must have realized, the linear terms will just become mean. So all the linear terms will become mean. This and these two terms will give us the fluctuating part. And there too, one mean, one fluctuation, when you take the average of that, will become 0. So this term becomes, so when we now move ahead, so this gives us equal to 0 is equal to minus d by dxi of mean of p by rho plus half uj plus half of uj prime plus epsilon ijk, which is it now, I have uj omega k and the last term. So let me write epsilon ijk of uj omega k plus uj prime omega k prime plus nu times d2 of ui by. See, this, if you have done the homework now, this should become fairly straightforward. How we got this derivative? नहीं ओमेगा नहीं है, अभी वेलोसिटी वाला इक्वेशन कौन सा वाला, ये लास्ट टर्म नहीं, अभी मैंने इसको वोटिसिटी इक्वेशन नहीं लिखा है. This is just the Navier-Stokes equation, the mean velocity. I've taken the equation for u. It's just the equation for u, written in another way. Okay. Viscous term अभी हमने ऐसे ही रखी हुई है. So this basically what will happen is, in the large scale, the reason why we have not played around too much with this is, when we do order of magnitudes analysis and when we are talking of the mean scales, this term will be negligible. We have shown at large scales the dissipation term is very small. This becomes active only when we write the u prime equation. So that's why whether you use omega or this term will be small. But this we have already argued for ui, not for omega I. And इसको मैंने वहां पे ओमेगा कर दिया था क्या उस वाले में इक्वेशन में? अच्छा, इसमें एप्सिलॉन भी कर दिया था एंड डी ओमेगा. ठीक है, तो दैट्स द सेम फॉर्म. बट दिस टर्म we have argued that in the mean, when we do order of magnitude analysis, this is small, the dissipation term, for the large scales. So now I think what I'm going to do is, if we look at the 2D flow, which means now we make it slightly more complex. So far we have done only pure shear, where u1 was a function of x2. Now we are saying both u1 and u2 mean are not 0. And also what we have is d by dx1 and d by dx2. Earlier we took only d by dx2, but now we say even d by dx1 will not be. But we also put a third condition. This is, so this what we have written is for two-dimensional flow. u3 is 0, d by dx3 is 0.
You took U1 and U2 mean to be non-zero.
Ah.
So just axis along U1 plus U1 I cap plus U2 G and make it again the same above case of one-dimensional.
Will it become? No, it will not be, because what will happen is, what you are saying is, because there are certain derivatives which are only along x1, certain only along x2. So if I write I think it's a good idea. What he's saying is, this is u1, this is u2. So now if we write the vector direction, you are saying this, and write the equation along this. No, but then this is for mean of u, but then the mean of u could change at each point. It's a function of x1 as well as x2. So if this is my whole domain, in which direction will I go? This will work only if they are constant. If it was a grid turbulence type of problem, that would have worked. But here this will not work. So then we look, but then also what happens is, if you have looked at the boundary layer type of flows, in boundary layer type of flows also we have d by dx is not 0, d by dy is not 0. But what we find is that the variation along the y direction or x2 direction is large compared to the variation along the x1 direction. Okay. So this is sort of seen that in boundary layer or jet type of flows, d by dx1 of the same quantity is much less than d by dx2. These are called developing flows. And in fact, these are the estimates which one makes if we look at the boundary layer. If I use the continuity equation tells me du1, d mean u1 by dx1 plus d mean u2 by dx2 is equal to 0. Now if I say d by dx1 is much less than d by dx2, then what I have to do is, there are only two terms in the continuity equation. Both of them have to be of the same order. So then what this will tell me is that u2 in such a flow, the developing direction is 1. Mean of u2 will be much less than mean of u1. Because continuity tells me du1 by dx1 is of the same order as du2 by dx2. u1's order I know. u1 will be the order with which the flow is flowing. So then u2 is being generated because u1 is changing with x1. And it is gently changing with x1. So therefore the u2 which is generated is if continuity has to be maintained, and if d by dx1 is much less than d by dx2, has to be of the order of, has to be smaller than u1. Or sometimes what you do is, this is what we do in the first course, d by dx1, if we write it as 1 over L, and d by dx2 as 1 over, let's say, small l, where small l is much less than capital L. Then du1 by dx1, this is of the order of u0 by L, and du2 by dx2 is of the order of whatever is the representative value of u2 divided by L, and continuity equation implies u0 upon L is equal to u20 upon small l. So u20 is equal to u0 times small l. This is order of magnitude of mean u2. So in such developing type of flows, you'll find the velocity flow is going in the x direction, major velocity is in the x direction, the mean velocity. There is a, because the velocity is changing with x, obviously it has to change with y also. So the y component of the velocity which comes in, if variation in x is very small, this will be of the order of x component velocity multiplied by L by L, small l by capital L, which will be small. And these two orders will be equal, what, d by dx1 and d by dx2. That is of order of capital L and small l, the ratio of these two. And that is the same order which the velocities also will take because of the continuity equation. Now, I think I'll stop here today. Now we have to continue. अब या तो ऐसा करते हैं, कल लेना है कि नहीं लेना, let's decide that. Let's, okay, if we don't want it tomorrow, then we'll make up later, but maybe not the immediate week, कभी बाद. Now, अब एग्जाम का जो कोर्स होगा उसमें I will not ask from vorticity. ठीक है? So before vorticity, आज वाला जो मतलब vorticity तो बेसिकली आज का ही लेक्चर है, या उसमें से थोड़ा ही मतलब उससे पहले वाला तो पूरा आएगा. जो पहले मतलब okay, let's say, let's take it till this point. Let's not be, we'll have till this point in the course. Let's not confuse things. ठीक है ना? That, because मैंने कहते vorticity नहीं आएगा, फिर कहा turbulence तो vorticity होता है, आपने vorticity पूछ लिया. So let's not get it till today's lecture. And that's why I'm not taking now tomorrow's lecture, so that we will take it afterward. There's no confusion. Exam mein I will not be there, but exam mein please, even if you don't understand anything, I don't think anyone will be able to answer any questions. So make assumptions and write. If there's something, calculator is a must. As you know, some of these things will have these powers and all calculations. Derivation एक आध कुछ हो सकता है. Derive an equation for u prime, ui prime or something. कोई नया equation दे दूंगा, इसका derivation करो. Things of that type you'll have to do. So that you'll have to, huh? पता नहीं अभी बनाए नहीं है तो नहीं, तो बता तो रहा हूँ मैं. Both, that's what I'm trying to say. भाई कैलकुलेटर मस्ट है तो डेरिवेट न्यूमेरिकल तो ही गए, डेरिवेशंस भी हो सकते हैं. तो बट इट इज ओपन बुक, तो हाँ 2 hours का है, so will not exceed. Get these numbers and then something we'll do starting from there. ठीक, हाँ. Let's try to, अच्छा एक एग्जाम का करके देखते हैं, let's see how it goes. अभी I'm sure things will be fine. बहुत प्रॉब्लम हो गई तो डोंट वरी, अभी लेट्स जस्ट फोकस ऑन ट्राइंग टू लर्न. ग्रेड की परवाह मत करो, आई विल टेक केयर ऑफ द, मतलब ठीक है, मतलब ऑब्वियसली आई कांट गिव ए टू एवरीवन, बट इफ यू आर रेगुलर तो पासिंग का तो सोचो भी मत. सबमिट योर असाइनमेंट तो मतलब इवन मतलब रीजनेबल, नॉट इवन जस्ट पासिंग, मतलब think that the grading will start from C or something like. If you are regular, then it will start from C or B minus. मतलब सारी चीजें देते रहो तो ठीक है, मतलब I have no issues. आगे हो सही. एक काम करते हैं, डाउट के लिए एक कल सेशन रख लें. टुमारो 12 to 1 आई विल कम हियर. जिनके भी डाउट्स हैं कल लेके आ जाना. ठीक है. I guess all of you are you staying in the campus or whatever. So we have a class hour anyway. So instead of saying we call off the let's whatever doubts you have, because तब तक पढ़ भी लेना. और अभी कुछ है तो नो कल क्या चीज अटेंडेंस कौन सी. हाँ कल की कंपलसरी नहीं है. ओनली दोज हु हैव डाउट्स विल कम. इट्स नॉट अ क्लास. If you don't, but or you can even send your doubts on mail. Yeah.
क्या मैं ये सही समझ रहा हूँ कि मतलब फ्लो समझो ये U1 है और ये U2 है, क्या तो फ्लो ऐसे कुछ जाना चाह रहा है.
मतलब सिर्फ नहीं जैसे एक बड़ा क्लासिकल केस होता है बाउंड्री लेयर का, where you have flow coming in like this. So the main velocity you have is the x component of velocity. But then it encounters a plate, suppose. तो यहाँ पे x component of velocity has to go to 0. So the velocity profile becomes something like this. So इसमें यहाँ पे तो this velocity is 0 here, and we get a sort of what we call, it's actually physically not that we call a boundary layer, where we say that यहाँ तो क्या है, flow can be treated as inviscid, the viscosity effects are not there. Then when it encounters the plate, near the plate the flow has to be, the viscous effects have to come in, because the velocity has to go to 0. And out, then some region away from the plate, you come across where the viscous effects are negligible. So here at this point, x component of velocity will become capital U. And this region is what we call as the boundary layer. Now this boundary layer, as you go down, its span increases. Because here it will be sort of just at this point, but यहाँ पे, in fact, even the boundary layer. So in that context, we say that in this, if this at any time is given, let's say the length is delta, and this length is L. Okay, so there we try to see what is the order of magnitude of delta over L. ठीक है. तो इसमें अभी हमें डेल्टा भी नहीं पता, एल भी नहीं पता, एल पता है. सो नाउ व्हाट आर द वेरिएबल्स, ऑर्डर ऑफ मैग्नीट्यूड हम निकाल रहे हैं, हमें क्या पता है. वी नो अ वेलोसिटी यू, कैपिटल यू इज गिवन टू अस. सो कैपिटल यू इज नोन, एल इज नोन. ओनली दीज टू थिंग्स आर नोन टू अस. सो आई हैव टू फाइंड द ऑर्डर ऑफ मैग्नीट्यूड्स ऑफ, लेट्स से द कैपिटल वी इज, और u0 है, v0 is the order of magnitude of v component of velocity, and delta is order of magnitude of y direction. Now as of now I don't even know is delta of order L. It could be. How do I know? अभी तो हमें केवल delta is a variable, and only two physical things I have are u0 and L. So now I go to my equations. So in my equations I write the continuity equation. So that is what I was trying to do here. That du, so u0 upon L will be of the order of v0 upon delta. तो अभी हमें, अब वहाँ पे तो I assumed in the class small l is much less than capital L, but I don't know that. So I'll just say v0 is of the order of delta u0 upon L. The second part के लिए we have to go to the Navier-Stokes equation. कुछ और था?
जो आपने जो लेक्चर में पढ़ा,
हाँ.
del u1 del u1 mean divided by del x1.
हाँ
जो कि x में वेरिएशन छोटा है बहुत x2 से,
हाँ
तो उसमें आप फिर उसको नाम दे रहे हो डेवलपिंग फ्लो, कि x2 में फ्लो डेवलप हो रहा है, ऐसा कुछ नहीं।
x1 के अलॉन्ग डेवलप हो रहा है ना. डेवलपिंग फ्लो में नॉट बी अ रियली वेरी गुड नेम. आई डोंट नो वेदर इट इज इवन कॉल्ड डेवलप. मतलब x में फ्लो बढ़े जा रहा है, बट दिस वेरिएशन अलॉन्ग x इज स्मॉल. सी थिंक ऑफ इट एज अ, अगर कोई ये डक्ट है, a small, very gently converging duct. So by continuity, you know U1 A1 is equal to U2 A2. So if area is changing very slowly, so the velocity will also change slowly in the x direction.
ये x2 में ज़्यादा वेरिएशन होने का क्या मतलब हुआ फिर?
So what is happening is x, because this x2 direction is small. So if I look at जैसे इसी वाले केस में, if delta is small, abhi I have not proved that, then variation of u along y will be of order u by delta, du by dy. U is u and y direction में the typical length scale is delta, and in the x direction it will be u1 upon L
तो u1 ये तो del u1
upon del x. Del u1 by del x2 will be equal to u1 upon delta. So del u2 upon del x2 will be mean of u2 upon delta. तो मैंने उसको सेम नहीं मानी है. See, that's what I was trying to tell you. If I say that order of magnitude along u2 is u2 0, so continuity equation में du2 by dx2 is u2 0 upon L, not u1 0, and these two must be equal. So this gives me u2 0 will be equal to small l upon capital L u0. That is what I said.
But like, so you are writing V naught upon L equals to V naught upon delta.
Huh?
This is that L, like capital L in the large cell still has an order V does not change, but delta will change exponentially, right? So is it fair to write it like this, or should it be defined point to point? That
So
we
now,
have
now,
V naught by X,
so now what you are saying is this delta is a function of x.
so it's a V naught X upon delta. Because V naught will also be scaling.
This is a scaling number है. Delta का क्या order है? For that what you do is we see. एक मिनट मैं इसको what, so this delta's order how do you get? अभी अगर V naught कर दिया, but we still have not seen how to get delta.
So we know that it changes, but we know that the changes exponentially.
See, एक मिनट, order of delta अगर उस तरह का flow है, तो then delta you can say is of order this diameter or square and the length is of this. But अगर इस ये flat plate boundary layer, that is where this question comes, that we don't have a scale for delta, and actually delta comes as a function of x only. And how do you do that? You go to the Navier-Stokes equation, and the whole premise of this region is that in this region what is happening? In this region the viscous term cannot be neglected. So now we have an inertia term and a viscous term. We equate the order of magnitude. So inertia term is u du by dx. Okay? And viscous term is nu d2u by dx square plus d2u by dy square. Now there it is the same u, one is with x square, one is with y square. So if we assume that we'll get y is much small, then d2 by dy square becomes dominant. So what you are equating is u du by dx is of the same order as nu times d2u by dy square. And from here you will get the order of magnitude of delta. Because u is of order u0, x is of order L, and so you will actually, if you do this out, is equal to at that L. if your question was delta is changing with x, so then L also will become x, capital L. Because if I'm talking of this, then I should talk of x, not L. So that's how then delta is a function of x. And if you say x is of order L, then it will become order L. Okay, so that is answering your question, and I wanted to, that's why I first went through this. So ये order of magnitude आता है boundary layer, which you would not have seen because you did not do a call, but तुम लोगों ने तो देखा होगा. हाँ, that is REL. हाँ, इस तरह से आएगा जब तुम करोगे ना, क्योंकि d2u सीधे सीधे ही करके देख, u du by dx square will become u0 square upon L, और ये हो जाएगा इज इक्वल टू न्यू टाइम्स u0 अपॉन डेल्टा. बस, हाँ, तो उससे याद. हाँ, ये क्लास में भी किया था हमने पहले. अच्छा, I don't remember. अच्छा, I don't remember. Delta will go like, yes, yeah. हाँ, delta goes like square root of L. क्या चीज? हाँ, अपॉन डेल्टा स्क्वायर, सॉरी, d2 by dy स्क्वायर, तभी तो स्क्वायर रूट आएगा, तभी स्क्वायर रूट आएगा, डेल्टा स्क्वायर होगा. So delta, in fact, that's why delta increases like square root of x. So that's why we show this boundary layer as growing with x. हाँ, हाँ, तो फिर बड़ा, तो इसमें क्या होता है फिर, this relation is valid only for laminar flow. So in fact what, but delta बढ़ता जाएगा, delta keeps on, so in fact eventually, but जो infinity जो तुम्हारी L वाली होगी, उसके मुकाबले डेल्टा विल बी स्टिल लेस. फिर तुम x भी तो बढ़ा रहोगे, x will go, delta will go as a very small power of x. हाँ, हाफ है. पाइप में क्या होता है, पाइप में दूसरा चक्कर होता है. एक मिनट यार, पर आज मुझे जल्दी भागना है, बट आई जस्ट, पाइप में क्या होता है, एक बाउंड्री लेयर यहाँ से आता है, एक यहाँ से आता है, इवेंचुअली दिस टू मर्ज एंड इट बिकम्स अ फुल्ली.
अगर मैं ये वाला हटा दूं यहाँ पे,
हाँ,
वाला हटा दूं, पर देयर इज सम सॉर्ट ऑफ मतलब,
हाँ, तो मतलब ये बढ़ता रहेगा, मतलब
बढ़ता ही रहेगा.
हाँ, बढ़ता ही रहेगा, बट कहीं पे फिर टर्बुलेंस आ जाती है, तो then basically this says eventually then the vortex, see also because viscosity is important, it turns out that vorticity is also important in the boundary layer. It cannot be neglected because du by dy है, तो vorticity तो आएगी. ठीक है, चलो आज कल